students of CET, because we have heard from him very nice talks in the past, some FDP programs. So let me give introduction to Sanjay sir from Niger. Dr. Sanjay Kumar Swain, currently working as Associate Professor in Department of Physics at Niger, Bhubaneswar. He completed his PhD from University of Hawaii, USA in 2004, and then he worked as research associate at Stanford Linear Accelerator Center from 2004 to 2008. Dr. Swain's research interest includes understanding the laws of physics at very fundamental or small scale through collider experiments, CMS experiments at Large Hadron Collider, and neutrino oscillations. He also worked on electron-neutrino appearance analysis in Minus experiments. During his PhD and postdoc periods, he worked on B physics experiment like Belly at KEK, Japan, then BA bar at SLSE SLAC, and Minus experiment at Formula. And today he is going to give his talk on topic Understanding Universe to Biggest Discoveries of 21st Century. With this keynote, I welcome Sanjay sir to give his talk. Hearty welcome you too, sir.
Thank you. Can you hear me? Can you hear me?
Yes, sir. Yes, sir. Yes, sir.
Yeah. And can you see my slides?
Yes, sir.
Okay, good. Okay, so I will talk about the understanding the universe, two biggest discoveries of 21st century. So with that, I will cover two topics. One is the discovery of Higgs boson, which we have heard for many times and we have been hearing, and it was discovered in 2012. Also, there was a wonderful discovery of a gravitational wave. Although I'm not expert in gravitational wave, I thought it would be very nice for people who are like exposing the undergraduate students or MSc students the two topics and their research potential. So I'll start with Higgs boson, and which so what happens is basically we try to understand in the laws of nature in the very, very fundamental scale. Means basically, if you take something and break it apart, make it smaller and smaller and smaller and smaller, what is the smallest component, and what are those particles, and how they combine together to form atom or molecules that you see around us. And so there are two ways. You have to first have a model for that, theoretical model for that, and then you would be able to, that model, you would be able to test it experimentally in some laboratory. So there is a quantum theory, and we call it standard model of particle physics, that describes how all the fundamental particles interact by a strong, weak, and electromagnetic force. I leave apart the gravitational force. I will keep it to the second part. And so people have been working on it since the last century. And so after many years of experiment and theoretical developments, the people found out that there are only, everything that you see around us is the visible part of the world, or visible part of the universe, that stars, planets, galaxies, earths, everything, like they are made up of only a handful number of particles, and these are called quarks. So there is UD, CS, and TB. There are 6 types of quarks, and there are leptons called electron, and then neutrino, muon is neutrino, and tau is neutrino. And each of these particles, they have their antiparticles also, particle and antiparticles. So everything you see around you, the visible part of the universe, is made up of only those particles or their antiparticles. In fact, the most visible part of the universe is made up of only three, U, D, and E. So up and down, that I below here I show, up and down make proton or neutron, and then you have electron going around and then makes the atoms, and then you get molecules and so on. So most of the visible part is actually made up of U, D, and E, only three. And there are some other particles like other quarks and electrons. They are available and they are detected in the cosmics and they can be produced in the laboratory, and people have seen. And all these particles have been discovered. All of them have been discovered. But the theory, so you build it, this is experimentally observed, and there is also theory involved in it. So the theory that makes all these interaction between the smallest particles complete the standard model, it requires one substance that is called Higgs particle, H, capital H written here. And the standard model says in order for this theory to be complete and make any sense, that is, and it would show that all the visible part of the universe makes any sense, for that you need that Higgs particle to be present, and it must be present. And people search, this theory was since last 50 years, 60 years, and till 2012, and people tried to search and they could never find. So they searched about 30, 40 years and they never found. So if you have a theory of standard model and it predicts Higgs to be there and you don't find, that's kind of incomplete theory, because that's one of the necessary ingredient of the theory. You find everything else, but you don't find the necessary ingredient. So eventually in 2012, we found, and that makes the standard model very complete. So what is the standard model? According to standard model, there are three forces. So I leave the gravitational force apart, but there is strong nuclear and electromagnetic and weak forces. And these are the force strength. And if you put two quarks, U and D, and they are charged particles, and they have between them there is strong force. They have electromagnetic force, and you find out how much the forces. If you take the ratio, that shows the intensity of the forces. And the only difference in particle physics and classical physics is normally when we say like there is two electrons and the one electron applies force on the other electron, it's kind of like this electron produces electric field and the other electron interacts with the electric field, and that's why we call force is equal to QE. But in particle physics, there is no such thing called electric field. We call it force field. There is no such thing called force field. In particle physics, the two particles interact with each other by exchange of particles. Like two electrons, they will be throwing photon at each other, or the two quarks, they will throw gluon at each other. So the two particles, they always interact with each other by throwing or exchanging particles among themselves. It's like two people throwing ball at each other, that's one here. So if the ball is heavier, you cannot throw it very far. If the ball is lighter, then you can throw it much far. So as analogous. So same way, the photons and photon is massless. So it can go infinite range because it's massless. So it can be thrown as far as possible. Or in other words, basically it has infinite range. So if the electron is in this part of the universe and another electron very far away, still there will be electromagnetic force. The weak interaction, there is you can see Z0, W plus, W minus, they are very heavy. So that's why you cannot, it's like you cannot throw them too far. So that's why the weak nuclear force is very short range. The strong interaction, even though gluon is no mass, but they have different reagents why they are bound into the nucleus. So it's more like a spring actually, so you cannot take it apart. So this simple description of particle physics where the two particles interact with each other by throwing or exchanging particles among themselves, and there are three kinds of forces, and then you build a theory and you make the predictions. Every time you make a theory, you make prediction. For example, Newton's law of gravity, and you predict like the value of G should come out to be 9.1 and then 9.8, then you go and measure it experimentally. If you experimentally find it's 0.13, then it's not a good theory, Newton's law of gravity. So if you have some theory, it should predict something, that you can go and measure experimentally in the lab and see, oh, yeah, this theory makes sense and it's really good theory. So standard model has been amazingly successful in describing the nature, and it has been tested at the Fermi level. When I say tested at the 10 to the power minus 3, 10 to the power minus 4, it's basically difference between experimental measurement and theoretical prediction. And they're very tiny difference, you can see. Very well, very good theory and very well measured. So that means we should just not, we understand the whole nature and the whole particle physics. We should not worry about anything, and we are complete in our understanding of physics. But that's not true, because the standard model is incomplete in many ways. For example, standard model does not have any mention of neutrino mass. So the standard model assumes that built on the assumption that a neutrino is massless. But we know that neutrino has a very tiny but non-zero mass. And the standard model cannot explain it because it doesn't even include the neutrino mass into it. Standard model doesn't talk about dark matter, which you know it is there, dark matter. It doesn't talk about dark matter. It doesn't talk about the dark energy. Standard model cannot explain where this why the electron is lighter compared to the top quark, which is top quark is like 200 or 175 GeV, electron is half MeV. It's a very wide range. Why electron is mass and the photon is massless. Standard model cannot explain why there is so discrepancy. Standard model cannot explain why the universe is dominantly made with matter, so there is no antimatter. What happened to the antimatter? Standard model, that's one of the experiments we worked on in the Bell experiment in Japan. But so there are many loopholes that standard model cannot explain. Although, so standard model is kind of like a theory that we can understand in a certain regime, but it cannot explain everything. So to me, it looks like, to us, it looks like a standard model is not a really complete theory. It is some part or subset of a bigger theory that really exists in the world. So we are basically trying to find out what is that a bigger theory that we should be looking at to, and that will basically explain everything that we can that many of the questions that I have put here, and there are many questions that is beyond than this also. And so standard model is probably the some low energy approximation of this some bigger theory that exists in the very high energy scale, and that we try to figure out. So how do you do that? How do you go on answering these questions or finding the answer to the questions that standard model has not been able to answer? Then you build an experiment that can go beyond the energy scale that standard model talks about. So that energy, so that experiment is called a Large Hadron Collider. So we call it a Hadron Collider because they take two proton beams and collide each other and smash each other. And when they smash, they just smash and burst, and then they just fall apart, and then you have a detector around it. It's a large because this proton, when we take it, it just it go around the underground, about 100 meter underground the Earth. So there is a tunnel which is about 27 kilometer circumference. And so the whole idea is basically you take in the 27 kilometer circumference the proton beams in opposite direction and then hit them, and they will just smash apart, and then just everything will come out. When they break apart and things will come out, and you try to basically put detector around it. And the energy that the energy at which they collide, they move very fast. So this is square root of AC center mass energy. But if you convert to the velocity, how fast they move, that is like 99.9999991% speed of light. So it goes like 11,000 times in 27 kilometers per second. So you can see how fast they move. So each blink of your eye is even 1 millisecond. So in each blink of your eye, it goes like 10, 11 times already. So that's how fast you can see. Very, very fast it moves. So let's see how does this work. So I just play a video here. So this is SORN experiment at SORN experiment at Large Hadron Collider, and so you have you create a proton from the hydrogen, and so kick out the electron, and it creates proton. Then you take those proton beams and put them in the different boosters. So you don't take a proton beams to close to speed of light right away. It needs to slowly pick up the speed. So it goes through many steps. So smaller to bigger radius. So you have proton synchrotron, then super proton synchrotron. Slowly it gets go to the higher and higher and bigger circles, where they gain more and more velocity or energy. And when they are very close to the speed of light, then we kind of inject them into the Large Hadron Collider, which is 27 kilometers. And when they are injected there, they go in the opposite direction in that tunnel you see. And then they smash. Each time they smash, you can see they just smash apart, and they just produce many things come out. And the whole idea is basically you catch them and see how it what it does. You can see that like they are. So every time the proton comes, they will just smash apart and particles will come out. Then after after few nanoseconds, the other particle will come, they will collide. So we don't take one particle, we take a bunch of particles. They will come and collide, then next come and collide. So every time they collide, the temperature of the energy is created is so energetic. So at that point of collision, it's so energetic. It's very close to the Big Bang energy. So basically the energy we create in that proton-proton collision, in that small space we create, is about 1 nanosecond after the Big Bang, whatever the energy was, we are creating the same energy. 1 nanosecond after the Big Bang. So basically what we are saying is basically we are creating a small Big Bang or small universe in that small space, and every little bit time we create one universe, then another universe. So in a small time. So the whole idea is basically, so when they smash and they come out, we try to study their property. And from that property, we can extrapolate, say like, oh, when Big Bang was created after 1 nanosecond, the same thing must have happened. So what is happening now, it must have happened same things there, because 1 nanosecond after Big Bang, the same energy was there. There was explosion, and we are doing here also explosion, and we are getting same energy as close to the Big Bang energy. So if we can find what in the physics here, then the same physics, the laws must have hold actually when Big Bang, just 1 nanosecond after Big Bang. That is the whole idea actually in our experiment. So we have actually every nanosecond we kind of like hit the protons and produce 1 Big Bang, and they smash each other. And you can see here, I will just forward and see, and we collect the data and see, you can see they collide, the proton comes, they collide, they make Big Bang actually. So again here, so protons come in the opposite direction, they produce Big Bang, and there is a big detector around it, you can see. And we just try to catch it and see what is the property, what kind of particles are coming out, or what kind of energy they're coming out, or what it means, and we just try to look for it. And when the two protons collide, then the energy in that collision point is extremely high. It's like 1,000 million times hotter than the core of the sun. So that is basically in that minuscule space, small space, and that's how much temperature it is, and that's the same temperature, just 1 nanosecond after the Big Bang. And this is just a real picture of the underground. You can actually drive with a small cart, 27 kilometer path, and this is sitting about 100 meter underground. And how big is the detectors that I showed? These detectors are, so around the collision point, there are detectors where we capture these particles coming out. How big is that, these detectors? So you can see this building is a 6-floor buildings. And the biggest detector is, so there are many experiments. So around the circle, there are 4 experiments. And the 2 experiments are doing multiple, they are called multi-purpose experiments. They can do many physics actually. And the other 2 experiments are very specific limited physics scope, like ALICE and LHCb do limited scope, but CMS Atlas can do many more physics. Atlas is the biggest one, and you can see they are like 6-floor buildings. That's how far the detector is. And CMS is like almost a 3 to 4-floor buildings. That's how big these detectors are. So they are underground, sitting 100-meter underground, and this is how big these detectors are. And this is the real picture. You can see the Atlas. And the center here where it is going to go, the beam is going to go and collide, and there will be collision, and there is around it in the cylinder, you can see there are detectors. This is not put together. It's still when it was installed. So this is open now, but there are right now you don't see all the clear pictures. They are put together, and there is a person standing there. You can see so house, and there are floors are there on the side. You can see the blue color floors. They're like 5 to 6 floors actually. This is how how big the detectors are. And then we just collect the each detector, like you have detectors, GM counter, and many detectors you have done in MSc experiments. Your detector is connected to the electronics readout board, and then you look at their signals. We have also many, each detector component has a readout, and then we look at their property or signals. But they are huge. Every nanosecond, if you have a particle colliding, then it's not easy to save all of them. So in fact, we don't save all of them. We actually, what we are interested in is very small fraction of the data. And so it is very important that we know which data to keep and which data to reject. We almost reject 99.999% of the data. There is very tiny fraction of the data we keep, and we just absolutely make sure that our logic, which collision to keep, which collision not to keep, is very well studied before we build the experiment and collect the data. And that's called the trigger system. And I'm not going to go over it very closely. So whole idea is basically when these particles come and they hit each other, then you collect. So that it's like same as a GM counter or any other detector. When you have like particles coming, or you have scintillators where the photon is coming and interact with the scintillation detector, and then you collect a signal. The same way we have a particles coming out from the collision, electrons, muons, photons, kaons, protons, neutrons. We collect them and we try to study their property. So one of these one of these things that one can study is basically look at the Higgs production. So if really from the 2 proton Higgs is produced, and then this one, so 2 proton collide, Higgs is produced, and then those Higgs decay to 2 photons. So you can get the information about 2 photons from the detector, and then trace back those information and combine those information and see that if that is consistent with being coming from Higgs or not. And that is basically shown in this plot, which I am not going to go very details. What I'm saying is, if you see a hump there around, if you see around 125 GeV of 2 photon mass, there is a hump. What it means is basically actually these 2 photons came through Higgs actually. And the rest of the ranges, you can see there is a flat thing, there is no hump. There is no hump means it is basically coming without any intermediate Higgs or any other intermediate states. So this is how the Higgs was discovered actually. So we have been trying to find out since ages or since decades is just the little bit bump there. And we could not see this bump for a long time. And so as soon as it was seen, this is how we call like the particle Higgs was discovered, because the 2 photons is actually coming through Higgs, and there is a bump there. If that bump would not have been there, still we would have said there is no Higgs. And why this bump means is that's a little bit more technical, which I can, if you question answer time, I can try to explain. And this is another Higgs where the Higgs can decay through 2Z and the Z boson. and then each Z can go to leptons. Leptons means muons or electrons and so on. And if you see a bump that you see here around 125 GeV, that means this is a Higgs actually. And you can see there is a bump there. So the black dot points are data we collected. And you see there is a really nice peak there that says actually. Yeah.
So we don't see any slides, only fast slides we're seeing.
I'm sorry, you don't see a slide?
No, only fast slide. So I think you forgot to show.
But I have been talking, I'm sorry, I have, you mean the title slide you are seeing?
Oh, only, that one was only showing.
Oh, excuse me. Can you see now?
Yes.
So, so far you never saw the slides, all the slides I have been showing. These slides you saw, right?
This side, only your initial fast slide.
Yeah, this slide, so this is Higgs photon, right? This you saw.
Continue. Because
Continue, okay. So this is the Higgs going decaying to 2 photons, and this is a Higgs going to another 2 for leptons, and so on. So, so basically, Higgs was discovered, and people now this brings the groundbreaking success to Standard Model, because this means basically Standard Model prediction of all the particles were discovered, and all the Higgs was discovered, and most of the Standard Model prediction experimentally. What when you have a theory that predicts some measure something, and we experimentally measure, not only see the particles, their properties. All these things were experimentally measured, and they were seen to be consistent with the Standard Model theory. So Standard Model is a very good theory. So what is the concept of this Standard Model theory? What happens there? The whole idea basically why we wanted to do that is basically try to the Standard Model being low energy approximation of bigger theory, why we think that way, and how we are going about it. The idea is basically, if you remember, like if you have an electromagnetic force. So electromagnetic force is like there is electric force and there is magnetic force. There are two different things. But eventually we realized that, oh, they are not two different things. They are actually two different manifestation of the same force. So if you take current and change the current, you get magnetic field. If you change the magnetic field, then you get the current in a wire. So they are actually not an electric field or electric force and magnetic force. They are not two different, completely different things. They are kind of entangled, and they are two different manifestations of the same one force. Actually, by changing E, you can get B. By changing B, you can get E. The same way, we thought maybe the electromagnetic and the strong and weak, they can be combined together, and they become, at some stage, they become one force. And then later on, gravitational, we combine gravitational force. And so what happens, our idea is basically, when universe started, maybe there was only one force. And then as it cooled down, they kind of branch out, they become different 4 forces. So we try to go backward and see, can we combine them, like now we know electromagnetic and weak, electricity and magnetism combined to electromagnetic force. Now electromagnetic force combined with weak force gives electroweak force. That's called a Standard Model. And then we combine with gravitational, that gives you a bigger theory. So can we go to that combined single force, which that during the Big Bang started with a single force, we think. So this is very similar to the, like why we think that way. It's similar what I showed in the left side. Like, you know, if you have a water that it's warm water or something, you can see everywhere it's uniform. It's no distinction. But as you cool down, then they make snowflakes. They make different structures. So maybe when the universe was warm during Big Bang, there was only one force, uniform one force, simple thing. And then the universe explosion happened. The universe expanded. It cooled down. and it becomes split into 3-4 forces. And we try to just go backward actually to study that property. And that has been going on for a long time, trying to find out, can we have just a single force? And what is the corresponding theory? What is the experimental prediction can we have? And we have not reached there yet. There are a lot of strong interaction we are yet to even figure out. Okay. So there are many more ideas of floating. So because the strong standard.
Sir, we could not see your slide. Sir, just there is a right top, there is a play option is there, slideshow. Click on that so that slide is not moving.
Slide is not moving.
So there is an option, right top play, slideshow. There is option right top.
Okay, just wait, just let me see. This is a little right top of the PowerPoint you are saying, and the PowerPoint.
Yes, there is a play option. There is
play. Oh, here play.
Yes, yes.
Now you can see.
So wait, not till now. There is not coming. No, sir, that is not coming.
It's not coming.
So you can do one thing that just you can do one thing. So each slide just you click so that it will come. So right now that is a click on the 14th slide. So we are seeing all these. Just click on the slide so that we will
can you see
see
15
all
now?
the slides.
Can you see 15?
Yes, sir. Yes, this is now. Yes,
okay.
Yes.
Yeah. Okay. I'll
just click on the slide, sir.
Yeah, I'll click on slide.
So that
I'll click on slide.
Okay. Thank you.
So there are many more ideas floating around, because the standard model we know is not a complete theory, and so people try to float around many ideas, many theory, and see if there are more ideas. But each of the idea, they should have their own experimental prediction. There are more predictions which can be tested in the lab or experiments. So if you are giving some exotic theory and that cannot be tested in the experiment, and then you know that's not a good theory, and then you throw them out. So many theories you predict, then some of them are crossed out depending on the prediction, which is not tested in the experiment. Okay. So that is what in the particle physics we are still struggling, and we are still trying to move closer, and hopefully that we'll see. We'll try to see how far we go. The next topics I want to talk about is basically gravitational waves. Can you see the gravitational wave slide? Can you see the slides on gravitational wave? Yeah. So next topics we want to talk about the gravitational wave. So the way we understood the way the gravity works is basically is, for example, if you have Earth that going around the moon, moon going around the Earth, so then you just or the Earth going around the sun, so you think that the Earth has a gravitational force that makes the moon basically that pulls the moon, and then it just goes around in a circle. That's what it says. So, and this was discovered by Newton, and by looking at the apple falling from the tree. In fact, that's not what really. So I always tell the students in the class, like, you know, if I take the apple and just drop it on the floor, how can you make a law like a force is equal to G m1 m2 over r squared just because apple fell? It's not a very trivial thing, like some pen falling from your hand, and you can write a theory like G m1 m2 over r square. It's not very easy. So it's not really true. The just apple falling made him discover that law. It is the most important thing is he understood the force that makes the apple fall on the earth is the same force that makes the moon going around the earth actually. And then he compared both of them and tried to find out G m1 m2 over r square. That is one of the things. I think in the backup slide I have put the whole how it was done. But anyway, so the moon is also the way apple is falling towards the earth, and the moon is also falling towards the earth. The only thing is, without earth, the moon would have gone straight here. And because of the Earth pull, it is just falling by about 0.14 centimeter every kilometer. So it falls a little bit distance. So something is going around the circle is also falling towards the center. Otherwise, it would have gone straight. So that is one of the things. But anyway, the Newton's law of gravity was very, very successful, and it was a fantastic theory. And till Einstein's special theory of relativity came. So the Maxwell showed that the thing we call light is rather a wave in contrast to Newton's corpuscular theory of light. And then he said Einstein published a special theory of relativity paper saying the speed of light is independent of a frame of reference. What is that supposed to mean? So what it means is basically, just look at this figure. So you have a vehicle going at a 60 kilometers per hour, and you are standing here on the left picture. So for you, it is going 60 kilometers per hour. But if there is another person who is going behind him at 40 kilometers per hour, he will not see that 60 kilometers per hour for the motorcycle. He will see only 20 kilometers per hour, because for him, he's rushing towards behind the motorcycle. So he will see less. It's like same on the road, right? If you're standing, there is a bus passing by, and there is a motorcycle guy going behind the bus. For the motorcycle guy, the bus is very less speed, right? If he measures. But that is not true for light. So for light, what happens, instead of that motorcycle, if you put a pulse of light, for me standing here, the light speed is c. But if there is a person rushing towards the light pulse by c/2, for him it should not be c, it should be just a half of c, because he is rushing c/2 just behind him. He cannot see the same speed, but looks like he also finds a c. So I am standing on the road, I see the speed of light, light pulse is c, and somebody rushing behind him, he also sees the speed of light to be c. And so the question is basically, and if he is going backward also by minus c/2, also he sees the speed of light to be c. So this is very confusing. Looks like the speed of light doesn't depend on whether somebody is standing or somebody is moving, doesn't depend. And it's very puzzling, actually. And that is one of the things we talk about, something called Lorentz transformation. So either what happens is basically the speed is measured by length and time. Maybe the length that I take the meter stick to measure the length, and I take the clock that to measure the time, is not same as the person moving. His meter stick is a little bit shrunk, or his time is going a little bit slower. So the way I measure speed is not the way he is measuring, actually. So my meter stick is very different than his meter stick, because he's moving, and we know all these things in the relativity. But one of the interesting thing I wanted to ask you, actually, what is the so the speed of light is independent of frame of reference. So what is the physical consequence we will have if one moves faster than speed of light? Really, if you move faster than speed, so we know nothing can move faster than speed of light. So what would be the problem if somebody moves faster than light? So this is made such a way that the theory that so any theory we make, it should explain our real world. We should not make a theory that just blunders our world, right? So what happens is basically, you think like if I am sitting here in my room and I think something is happening, or if I find like I shoot a bullet and it hit you and you got killed after 2 seconds. But if you go faster than speed of light in some space shuttle, for him it would look like if that person is moving faster than speed of light, to him it would look like you are already killed and I have not even shot my gun. And that's not, you don't want to build the theory that I have not even shot the gun and you are dead. Or same way, like, if there is a mother, then there is a mother, and then after 20 years the child is born, but you are just going in the speed of light and you find the child is burned, but there is no mother is not burned yet. You don't want that theory to be there, which really makes no sense and blunders the world, right? So it just reverses the cause and effect. So that's why the speed of light is, for good reason, it makes sense. You should not have anything moving faster than light. Now the light travels, very close to the 3 lakhs kilometers per second. It takes about 8 minutes to reach. The question is now here: if the sun is giving light and it takes 8 minutes to reach to the earth, if the sun vanishes right now at this instance, when will the earth know if sun vanished or not? Because if the sun is not there, the earth has to move straight, because there will be no gravitational pull and earth would just go straight. So the earth should know that sun is not there. Okay. So if sun is there and all at a sudden it vanishes, when will earth know that, okay, now sun is not there, I should move straight, I should not go around, move around, because there is no such thing in the center. So it looks like earth would know only after 8 minutes, because the last light that comes from the sun will reach at the sun or the earth only after 8 minutes. So earth would still go around in a circle for 8 minutes till the even though sun is not there for 8 minutes. However, the Newton's law of gravity says as soon as the sun is not there, the earth should go straight instantly, because if the m1 is not there, then the force is 0, because F is equal to g m1 m2 over r square. There is no time. So if the m is 0, so mass of the sun is 0, the force is 0. At that instant of time, there is no force and the earth should move. But how can it happen? For earth to go straight, earth should know. There should be some communication between sun to earth, and it should take at least 8 minutes, because nothing can travel faster than light. So even the light carries that information, it should take 8 minutes. But Newton's law says no, it would be instantly, because the mass is 0 and force is 0. Earth should move instantly, and that's the problem. So then that rescue to then there is, so that was one of the flaw of Newton's law. And there is another flaw of Newton's law, is basically perihelion shift of Mercury. So if you know this sun and the Mercury going around, and they don't go in the circle, they go in the ellipse. And the perihelion is basically the closest point to the sun. So it goes like this and then goes in the thing. So the perihelion, every time the perihelion moves, okay. And the Newton's law of gravity predicts how much it moves, and then the experimental measurement shows like, no, it doesn't match with Newton's law of gravity. There is a very tiny discrepancy between what Newton's law of gravity says and what we measure. So that's why, so there are flaws actually in Newton's law, just to, if you want to. So when you say this law is wrong or this theory is wrong, so the theory is correct for a long time, but somebody comes up and sets up an experiment that makes more precision measurements, and then finds out, oh, this law is what this theory predicts is not really true, because I just so you go to like 5th decimal place, then you find out there is a discrepancy, then you say, oh, this theory is wrong. So it depends on actually how experimental accuracy you can go in order to prove that this theory is not a correct theory. So then comes the rescue, is called Einstein's theory of general relativity. So for the Einstein's theory of general relativity, it basically says there is no force between two particles. So the moon is going around the Earth because the Earth is so heavy, and it creates some curved, that it just makes the wrap, the space just kind of like makes it's not a flat space, it just makes a wrap, and then just the moon is basically trapped in that thing. So I'm showing a video here what happens. So you can see the Earth, and then Earth creates some wrap, and then the moon is trapped around it. And similarly, the sun is creating a bigger one because it's much more massive. It creates a bigger curvature in the space, and then in that bigger curvature, the sun and moon, both of them are kind of like bound, so they cannot escape. They have to go around, but it happens just because of the curvature of space and time. It's nothing to do with a gravitational force between these two particles, and that's the concept actually he discovered. And one of the predictions of the and it predicts a perihelion of Mercury to a very good agreement. Also, it predicts when you have a theory, it should have many predictions. It predicts like the accelerating mass. When the two masses or one mass goes around a very high speed, it accelerates, and it kind of radiates a wave, and we call it gravitational waves. It's like a accelerating charged particle gives out the photons, right? So when the charged particle accelerates, it radiates photons. The same way, if you have a mass, it moves around, it gives the gravitational waves, and we should be able to measure that gravitational waves. Okay, so how do we measure those gravitational waves? So you can see here that there are two masses, two big black holes, and they are moving around, and when they are basically going around around each other, they are accelerating. They kind of radiate these waves, gravitational waves, and these waves kind of travel in the space, in the universe. They go actually very long time ago, even though it was created, they travel in the space. At some point, they will just cross our Earth, or they will go through our Earth here, and then they will just shake the Earth, because it will just stretch. So when the gravitational wave goes, this basically expands, and so it's like wave goes, so it just expands and compresses the space. So if it expands this way, it will compress the other perpendicular way, and if it expands compress this way, it will expand the other way actually. So because of the compression and the expansion of the Earth, so because the Earth is inside the space, so you will be able to see actually this compression and expansion. So if the gravitational wave goes through the Earth, you can look at any 2 points, then the distance between them is going to change, and they will just move like this, compression and expansion. So the whole idea is basically find out actually, take any 2 points and see, do they actually compress and expand or not in the periodic manner actually. So for that, you have to have a 2 perpendicular experiment, which I'll show later. So what you see here is a little bit, you can see the Earth is moving, and here it shows it's completely exaggerates. I mean, it's really a pictorial way, but that's not what happens actually. I will tell you how much the space between 2 points change, but you can see they shake actually. So how do you see this this gravitational wave through this Earth or not? How do you measure it? So this you measure it, you build an experiment here. As you can see, there are perpendicular arms here. There are 2 experiments done there, and one is basically Livingstone here, LIGO, and there is Hanford. And there are 2 experiments, and they are very far away. And each experiment is like perpendicular arms. So if the gravitational wave goes this way, it will just compress, and the other way it will expand. If this way it compresses, the one arm it expands, the other arm it compresses, and that other arm it expands, this arm it compresses. And we want to see that compression expansion. So how do you see that compression expansion? You just send the light. So this is the perpendicular arms. You send the light, and then you see how much the light takes. If they are exactly same length, the 2 arms are same length, they should come and hit the mirror and come back, and they should come and hit the mirror, they would come back, and they would come back to the same at this point, the origin point to the same time. So I'm going to show you the pictorial here again, very simply what happens. So here you have you shoot the laser light, it goes in the perpendicular distance and it comes back. If the length of the 2 arms are changed, expand and compress, then you will see, like you see here, there is laser light, the way it goes to one arm, the other component goes to the other arm, they reflect from the mirror, and they will come back, and then they will go to, and then there will be interference between 2 arms, 2 here. And if they constructive interference, there will be more light. If that destructive interference, there will be dark. And you can see here, when they come back, so So here it shows, you can see there is constructive and destructive interference because of the change in the arm size, and because the distance between 2 points will change, and you will see like light, no light, light, no light, light, no light. So there, because of the constructive and destructive interference. So by looking at the light, no light, you can find out actually how much the distance it changes, or if there is any gravitational wave went by or not. So how much it changes? So the experiment that was built here is actually each arm is about I think it's 4 kilometer arms, and so if you have a gravitational wave that goes through Earth and Moon, it changes the distance between Moon and Earth by how much the one proton is. That's how big it will change. So, or how much is one atom. So I think if you take from 4 kilometer arm, the amount of the compression and expansion it would have is basically smaller than the size of the even proton, 1,000 times smaller than size of the protons actually. And that is how small distance. So this is the LIGO sensitivity. You go to about 1,000 smaller than the size of the protons. And the proton is about 10 to the power minus 15 meter. That's the radius, and 1 femtometer. And the LIGO can measure the sensitivity about 1,000 times smaller than the size of the proton. So if you have some light going and coming back, and there is a light going and coming back, if the distance changes by 1,000 times smaller than proton size, proton radius, still it can measure that little size. So you need to be very careful actually to see that little size is, because if you have some train or bus going in on the top of it on the experiment, that can vibrate, and even that can be much larger. That's why it is very important to have 2 experiments, because if the really gravitational wave went passed by this Livingston, and it is going at the speed of light, after 10 or 7 milliseconds, you should be seeing the same gravitational wave effect in the Hanford, right? So if it is really coming from some natural things like some earthquake or some vibration of the train, it's very unlikely like after 10 milliseconds, there will be another train there in the Hanford, right? So that's why you need 2 experiments so that there is a correlation, and there is exactly, right now I see something after 10 milliseconds, I see the same effect there. Then you know it is actually really coming from the gravitational wave. And people try to measure in the control room, and with the way we have experimental data, there is just some experimental data. And I cannot send you the sound here, I believe, because you cannot hear the sound. So you can hear if there is a really some constructive destructive interference pattern. So it's like a wave, and you can make this is kind of like, and you can make some magnify or amplify this the signal and try to hear that sound. And you would be able to hear the frequency of the sound or the amplitude of the sound. So if there are 2 masses, black holes, half the solar mass, they would give you different sound than half solar mass with a 2.5 solar mass. So if you have 2 black holes with different solar masses, the different heaviness, they will give you different sound. So you can hear those frequency, or from the experiment you can look at the frequency and predict actually what happened if there is a really gravitational wave passed by. Actually, is this coming from what kind of black holes going around what, and how far they are. So in fact, people here is one of the sound you cannot hear, but I can see this is the sound of the Hanford and Livingston together. They see after 7 milliseconds. And that I'm not sure if you can hear, but that you can look it up on the YouTube. So people have heard this sound, and from this frequency, you can actually predict. You just say, oh, what happened? Is it really gravitational wave? And looks like yes, the same signal arrived 7 milliseconds later at Hanford, and the signal was so you make a model and see like which model makes this frequency match. And looks like there was 2 massive black holes. One is 36 times mass of the sun. Another is 29 times mass of the sun. And they merged together and they made it 62 times solar mass. But the rest 3 times solar, 3 times the sun mass was kind of used to radiate this energy. So that mass get converted to energy, and then it was like gravitational wave just radiating, and that is what we saw actually, and it happened about 1.3 billion years ago. So in summary, there is a lot of science under study now. We are starting to understand nature, but we are very far away. We just did the electromagnetic and weak interaction, combine them together. We are still running the LHC. It will run for another 15, say 17 years. And then after that, there will be more new experiments. The LHC is now, it's 27 kilometers. Now it is planned to make it to about 100 kilometer radius, 100 kilometers circumference underground. It's huge, and there is a plan for that. And there is plenty of science to be studied. I hope that some of the new people, new students who are entering, you will have plenty of opportunity to study this. And for the LIGO, it was a fantastic success for the Einstein's general relativity, and people have been, and there is a experiment actually that is planned, actually led by IUCAA Pune, and they are planning actually to establish similar to LIGO experiment in India also. And thus I think the place is already chosen, and people are already, the activity is going on. So I think by the time many of you students are ready to do PhD, there will be plenty of opportunity to work in the experiment, LIGO experiment within India, outside, as well as particle physics. Thank you very much. Thank you for listening.
Thank you, sir. Thank you for unraveling some of the mysteries of the universe in a very listed way. So there are a few questions in our chat box. So I'm going to read out for you. So kindly respond to. So there is a first question by Niharika Mohapatra. How does the Higgs field give mass to a particle?
So it's a very, so what happens is, I did have one video. I should have done that. So when the universe started in the Big Bang time, so it is the theory, the way it works is basically everything was massless, but as the so at a certain point, this Higgs field, about 1 nanosecond after the Big Bang, the invisible fluid appeared by itself. It just appeared from nowhere. So it's very similar to superconductivity, right? So you cool that, there is material, and then you cool the temperature to lower temperature. At certain point, you have superconductivity, and there is a Cooper pair and new states of matter. The same way the universe expanded and cooled, and at certain point there was a new state of new condensation appeared, the way you have a superconductivity condensation. So this new condensation appeared. We call it Higgs field or Higgs fluid. So everything that was massless, all these particles, they enter to that fluid. So as they enter to that fluid, they feel that interaction with that fluid, and through that interaction, they gain the mass. Some of them don't interact as effectively, but like photon, they went through that fluid, but they never experienced the presence of that fluid. So they were still kept as massless. But the electron, when it went through that, which was supposed to be massless before, when it went through, it experienced very little less interaction. That's why it's less mass. But the top quarks, when they went through it, they experienced a lot more interaction. That's why they had more mass. It's like a fish in the water. So if I am going inside the water, then I will have very difficult time to swim. So I will face the resistance. But if it is a fish, it would have very easy time to go through it. The same way the photons and electrons, they have very easy time to go through it. At least photon had no interaction, electron had less interaction, and some particles have more interactions. They have more heavier. That's how it works. But in a theoretical model, there is all these masses come from some interaction, and these interactions are described in standard model, something called Yukawa interaction. And that Yukawa interaction, you can experimentally measure it, and that's how you say actually it is coming from the Higgs particle or Higgs field.
Thank you, sir. So there is another question by Arunima Swain. She's asking related to the graph showed on Higgs boson. So she's asking why it is necessary to have high sigma precision to confirm that the Higgs boson exists.
So if I understand question, he's just saying why it is necessary to have more precision, right, to confirm something. Yes. Yeah. So look, I think look at this plot in the left side I'm showing here. If you have so in an experiment there is you can see the red lines. Red lines are not from Higgs. There are 2 photons coming not from Higgs, but there is a little bit bombs which is coming from Higgs. The question is basically every measurement, every data points there is an error. So the question is, if I have some background which is red line, I'm going to basically the error, I'm going to fluctuate the error a little bit. So if I fluctuate by 1 sigma and it matches with my that peak, then that peak is not even Higgs. I can say it is there is some chance that it is just a background. So for the peak to be clearly visible, it has to really have a big peak. And there should be, even though I fluctuate that there is a red line, if I fluctuate by a little bit more, still that peak should be very clear. So in the precision language, we call it like you have a much more sigma, 5 sigma, 7 sigma precision. That means you have a much more clear peak. And even though you fluctuate this background, you take the background and move it up by 1 sigma or 2 sigma, still your peak is still there. But if your peak is very little bit, then you fluctuate the background, it will eat up all the peak and you don't know whether it's background or peak. So that's more of a technical things, but in a simpler way I can explain like, okay, I mean, if their peak is very smaller with a less sigma, you don't know whether it's a fluctuation of background or it's really a signal, Higgs signal.
Okay, so there are many more questions, but I will take one last question. So let's say, so sir, is it possible to explain gravitation from the Higgs boson?
The Higgs boson has nothing to do with the gravitation. The Higgs is basically the Higgs concept of Higgs comes from the standard model, and the standard model is the interaction between electromagnetic and electromagnetic and weak forces. So the standard model does not include the gravitation. So Higgs doesn't talk about the gravitation at all. That's why you have to look for something beyond the standard model and see if that can explain the gravitation, and there is a bigger theory. That's why you want to go beyond standard model, because it doesn't talk about gravitation.
So with this, once again, I thank you very much, sir. Thank you.
Thank you. And those students, if you want to ask some questions, and you can still look up my NISER website, and if you have some questions, you are welcome to ask by email, or if you have you want to ask something over the phone, you can get my phone number from your head of the department, and you can just we can discuss more, and I'm fine with it. Thank you.
Thank you, sir.
Thank you. Bye bye.
So, Kartikeswar, sir, can you please share your slide?
Yes, sir. So I'm just sharing that now. Are you able to see the slides, sir?
Yes.
Okay.
Yes.
Okay. So should I keep it in this mode or in a full screen mode we should continue?
Full screen also. Yes.
Okay, so let's hope that this is visible, the full screen is visible to you all.
Yes. Yes, sir. Let me start introduce.
Okay, okay, all right.
Right. Let's move to our next class. I, Dr. Jayakishan Khattai, on behalf of Department of Physics, CET, take the opportunity to introduce our next speaker, Professor Kartikeswar Senapati. Very good afternoon, sir.
Good afternoon.
Senapati is currently working as a reader in physics at NISER, Bhubaneswar. Professor Senapati did his master's from Department of Physics, Uttar University, and completed his PhD from IIT Kanpur. Subsequently, he did his postdoctoral research at University of Cambridge, United Kingdom between 2006 to 2011. He is an experimental condensed physicist and specializes in superconductivity and magnetics. He has many contributions in the areas of pressure consumption and spin flow. Today, he is going to talk on a very interesting quantum phenomena, the proximity effect in condensed matter system. The title of his talk is Superconductivity in Magnetic Proximity. With this, now I request Professor Senapati to deliver his talk. Please.
Thank you, sir. Thank you for giving me this opportunity. I hope my slide is visible to all of you. Okay, I'll just put my video on also just to make it. Okay, so my slide is still visible, right?
Yes, sir. Yes.
Okay, thank you. So let's see. Good afternoon to all of you. This is a very good initiative. I think Professor Oza said when he told me about this, I thought this is a good opportunity for students to get an overall exposure to many of the advanced fields in physics. Throughout the last few days, I have seen some good talks also. Just now also, Professor Sanjay Swain gave a good introduction to high energy physics. From there to here, we have to. It's a big shift of gear essentially, because that is a very high energy phenomena that Dr. Swain explained. But we will be talking about low energy condensed matter phenomena. So it's really a shift of gear. Okay.
Excuse me, sir.
Yes.
Sir, please make your video on, not visible.
It is on. To me, it looks like okay. It is on. So let me stop presenting and then restart. So. Am I visible or not? It's on actually. No.
You are visible. Yes.
Okay. So okay, my slide is probably not visible right now.
The slide is not visible.
Yeah, that's what I want to say. Okay, slide is visible now.
Yes, sir. It's okay.
Okay. Sorry for this discussion. I hope both video and slide are visible right now.
Yes, both are visible.
Okay.
Thank you, sir.
Okay. So today we'll be talking. I'll be discussing a little bit about superconductors in magnetic proximity. So I think yesterday or day before, Professor Anil Kumar introduced a field in this forum. He introduced a field called spintronics. So which is has been very active since last 30 years or so. and for obvious reasons, because with charge-based electronics, we see that there is a roadblock. We cannot move ahead. And there is a limit to it. So what next beyond charge-based electronics? The normal electronics, I mean. So next is basically to exploit another degree of freedom that we have with these electrons, which is the electron spin. So Person Anil Kumar actually nicely introduced that subject. So what to put today's discussion to the context, what I'll do is I'll start with where it fits in. It's kind of in a way you can think of it as a continuation of what Professor Anil Kumar said. It's a spintronics is an evolving field, and how superconductor has come into spintronics. So that is the overall, the bigger picture of this today's presentation. So I have kept it simple at a very simple level for discussion, because many students I see are attending. So there will be not much technical data, but I think the motive is to introduce the field, so to get people interested rather than going into the nitty-gritties of the data and analysis of that data. So in that spirit, so I'll just introduce the context, and then what are the general issues people are there are issues with the field. By the field, I mean spintronics with superconductors. So there is a name for it, superconducting spintronics. So what are the issues? And then finally, in last 2-3 slides, I will just show some of the experiments that we are doing. Of course, it's a very big field, but some aspects of those superconducting spintronics area we are touching upon. So I'll just give a brief overview of that. A couple of experiments that we are doing. Okay, so let's start. So as it has been already pointed out, spintronics is when you use the spin degree of freedom of an electron in a device. Okay, so that is in a solid state device, you use the spin. So these two effects, that TMR and GMR, Professor Anil Kumar has already introduced. It's at a very basic level. GMR is, the picture says, as it shows, if an electron is going through the 3 layers, it is shown as you can see on the right hand side. If the magnetization of the ferromagnetic layers, which are top and bottom layers, so that is those are aligned, then the electrons feel less resistant. If they are anti-parallel aligned, then the electron feels more resistant because of the scattering. So in a way, it is an effect which is the moment you see there is a change in parallel and anti-parallel configuration. So immediately you have a device, you have a structure, which you have an on-off switch. Okay, so that becomes useful immediately. So now, how big this effect will be, so that depends on the exact technology, but the bigger the effect is, of course it is more useful, because detecting that effect becomes easier. So you don't want to go work in the limit of error bar, so that if there is, let's say GMR is 1%, and so change in resistance is 1%. So detecting that change in resistance, you need more high precision voltmeters or the equipment to detect with certainty. But if your TMR or magnetic resistance effect is all, let's say 100%, so then you, with a primitive voltmeter, you can measure. So that is the idea. So an improvement over GMR was the tunnel magnetic resistance. So here also the concept is same. So
Sir, may I interrupt you?
Yes.
Sir, can you make the slide full screen mode?
Slide, sorry?
That is, the slides are not in the slideshow mode. It's not coming in the full screen.
Okay, so let me. Now?
Not yet.
Okay, so I have done it full screen. Still not?
Still, I don't see.
Okay, I mean, do you see the slide at all, or it's in the?
Which slide? Yes.
Okay. I think this is.
I think you have to go to that slideshow icon on the
Okay.
below. Sorry, below the.
So no, that though I did. So here, no? Here.
I think at the left hand side below. Sorry, right hand.
Right hand side below. So that's what I clicked. So okay. So it's a bit strange because I have clicked.
Yes, that one.
No. Okay, so let's. Let me.
Yes, that near the percentage of battery. Sorry,
This one,
yes.
right? This one. Yeah. So that I am already pressing. So I am seeing it full screen actually.
Oh, you will see there.
Should I continue or should?
Okay, okay, sir, you continue. Okay.
Okay, so to continue, so this TMR effect, as it has been pointed out already, this is much stronger effect because here the electrons, the gap between the two ferromagnetic layers is actually a tunnel barrier instead of a normal metal like in GMR effect. So in that case, it is a much sharper and hugely enhanced magnetic resistance, which is a better switch compared to GMR. So these are, there are many more advances in this field which are happening. But one thing what I want to point out here is that they invariably use a ferromagnetic layer. So that is in a way the requirement for any spintronic device, because you need a spin polarized current in a way, so which these ferromagnets actually are able to give, because they have as a source of polarized current, so there is no escape from this. But then why you want to put superconductors into the spintronic? Let's say what people are trying to do, just like in normal electronic devices, people have been reducing the size of the devices. Similarly, spintronics devices size also people are gradually reducing. So to what extent it can go? So it is always limited by the heat that will be generated. Although it is a spin-based device, but still there is a current which is going through the material, which generates heat. Okay. So heat, which is I square R component, there will be some current, so there will be always some heat, no matter how small. But when the devices themselves become small, the small amount of heat also becomes, considerably, considerably effective in damaging the system or damaging the functionality of the device. So one way out of this is that you, instead of a normal metallic reasons, you use superconductors as a, because they have, for the obvious reason, they have zero resistance. So there will be no heating in a way. So the device itself will not be heating due to the operation. Of course, you have to, because we don't have a no room temperature superconductor yet. So we still have to use the superconductor which are which are very low transition temperature. So you have to operate them at low temperature. But in the device itself, so there will be no heat generated due to the current which will be flowing. Because current is inevitable, so that you have to flow anyway. So that is the reason. So can we take care of the heat part by introducing a superconductor? That is why superconductor came into the spintronics field. So this is, this is good. The concept wise, this is good, everything good. But then, okay, so this is what I already told. So superconductors are essentially zero resistance. That you have seen this graph probably a number of times. So this famous Kamaligon's graph. And this is the fact that we want to use in superconductors. So that is why this new field, spintronics, has come. And so this is all. This is a good thought, of course. But how to implement this? How to go about it? So that what it boils down is that you have to, spintronics device, you already have a ferromagnet and you have to put a superconductor next to it. So that is the requirement of the field. So then what are the problems? What are the, I mean, in general, so there are some experiments already in terms of spin valve kind of geometry. You see the devices that are shown in the right hand side. This is a similar concept. Here you see between two ferromagnets, there is a superconductor instead of a normal metal that we had earlier in the GMR effect and normal spintronic devices. So in the parallel and anti-parallel configuration, when it is parallel, it can drive the superconductor into normal state. And when it is anti-parallel, because the magnetic effect is weaker, then it can remain in a superconductor can remain in a superconducting state. Okay, so you can see the right-hand side is the far right is the when both layers are aligned, both ferromagnetic layers are aligned, then it is strong. So the superconductor, there is a thin layer of superconductor which is feeling more field in a moment next to it. So it is going normal, okay, because superconductors are they respond to the magnetic field. And in the left one, you see that they are misaligned and they are anti-parallel aligned. So it is into the superconducting state. So the change of resistance, I mean, you can say magnetic resistance is actually infinity because it is from 0 to some value. Okay, so it's a extremely good switch in terms of any standard. So 0 resistance to some finite measurable resistance is very good. But it is, of course, this has to operate at low temperature, but the switching effect is very good. And it works in a very small field, like 10 to like 50 to 100 Gauss only. Okay, so this is initial experiments. You can say this was to proof of the concept that, okay, you can have a switch with a spin valve-like arrangement with a superconductor. So that was the initial devotion. So this triggered a like field. And so far so good. So these are all good. But then the biggest issue is to take this any further, right? This arrangement of superconductors any further beyond the spin valve structure. The biggest issue is that conventional superconducting order and ferromagnetic order, they don't go well with each other. Okay. So what I mean by that, it will become clearer in the next slides. Okay. So what are the issues? So I'm coming to the issues of the field. Then. Major issues, and I'm not going to the very much. There are a lot of small like technical issues which one has to solve actually to take this field anywhere near a good functionality. So in terms of the field, this is still in a primitive state. Okay, so we are not nowhere close to a real application wise. It's very far away. But you have seen that spintronics is already in use in the reed heads and other things. Normal spintronics is already in use, but this is very far. Okay, so let me point out. So there are three things I would like to point out. One is conventional superconducting order and ferromagnetic order. They don't go well with each other. Second one is for spintronics, you need a spin polarized current to, okay. So that means you need some polarization, but the superconductor has Cooper pairs. I'll explain a little later what it is. Cooper pairs, which are essentially made up of spin up and spin down electron pairs. So that means the net spin is 0. So there is no polarization. So it's useless in terms of spintronics unless it is polarized, unless the material is able to handle polarized current. It is useless for this spintronic application. So that is one thing. So then other thing is that there is this interface issue. So this is a very different kind of superconductor. Is a very different kind of order compared to magnetic order. So the interface issues are always there. If you make multiple layers in a thin film, usually people make various techniques. People use thin film depositions. Always. So there is some interface issue which limits the performance of the Yes.
Yes, sir. Actually, slides are not moving. Can you just
Okay. So maybe I do it in this mode. Okay, so this is, I'm at slide number 8. Are you able to see?
Yeah, we see in that reading view option. I think the one you are clicked here, it is the reading view option.
Yeah.
And you
But
just on the slideshow.
Slideshow, then it is taking to the full screen. And
Sir, can you click on F5? F5.
it is a full screen.
Yes, sir. So is it showing your full screen in your screen?
Yeah.
So actually, there is
So-
problem. That is not coming. So there's this reading mode side is okay. So just to continue. So now it is showing slide number 8.
Okay, so in this, let's see, slide number 8.
Okay.
I'm changing. So this is slide number 8, okay?
So this, yes, sir.
Okay.
So go through this. So we will see.
Yeah, okay. So I have pointed out the issues. So then let's go a little deep into the actual real issues at the microscope. So this, you can see here, the basic thing about the superconductivity is the pairing of electrons, which was called Cooper pairing. And it's a momentum space pairing. It's not like a real space pairing that it's generally, I mean, students get confused with this. It's not a real space pairing. So these are electrons, spin up and spin down electrons with opposite momenta. So they come with a net center of mass momenta as 0. Okay, so they pair up in a momentum space. So because they are paired up, so they are no more as a pair. They are no more in a no more fermion. So as a pair, it is a boson. So if some of you must have done a little bit of quantum mechanics, the bosons can condense into a single state. So that is what happens when the material goes into the superconducting state. So into the superconducting state, you have this because this is paired, and the entire system, all the Cooper pairs are in a single state. You cannot, you cannot scatter anyone arbitrarily without affecting others. So it is so the resistance as such is the normal resistance that you see in normal OFs that doesn't come into picture. Okay, so this is the essential ingredient. So in a superconductor, you have a Cooper pair. Okay, so now in a ferromagnet. So I'm at slide number 10 now. I hope it is visible. So in a synchronic system, you will have a ferromagnet. So we know very well what ferromagnets are. That there will be and there is some exchange field in the ferromagnet which aligns the spins in all spins in a domain to a single direction. Okay, so this is where the disparity comes between the superconductor and a ferromagnet. Superconductor tries to make pairs with up and down spins, and ferromagnets tries to make spins all parallel. So that is where the conflict comes in, and that is where that is what one has to deal with. Deal with means you have to understand this process to take this field any further. Okay, so this is so the picture at the bottom of this slide is domain wall. I think all of you are essentially familiar with it. So if you have a ferromagnet, you will have a domain. Okay, so that is. I'm just pointing out here because later on. I'll be during the last slides. I'll talk a little bit about domain walls. Okay. So let's see. I pointed out 3 issues. So let's see what can be done about the first 2 issues. First 2 issues boil down to the same thing. So can we have, if we have a, if you have a long range superconductor, supercurrent. So it's like, okay, so this is a bit. So what happens is that if I go back to the slide, this Cooper pair, so this pair thing, if it goes into this ferromagnet, because the ferromagnet tries to align both the electrons of the Cooper pair into the same direction, that is a stronger force. So then it breaks the Cooper pair. So it doesn't remain the Cooper pair anymore. It becomes normal electron in a ferromagnet. So that essentially happens at the interface of a superconductor and ferromagnet if you put them together. Okay, so so I'm just a little bit explaining what that is. So it's this if you put something next to the superconductor, let's say normal metal. I'm at slide number 12. Let's say normal metal if you put next to the superconductor. So what is happening? The superconducting order parameter. So there is some leakage of Cooper pair into the normal metal. So some Cooper pairs leak into the normal metal. That is inevitable. But how far they can leak? So it is there is people have done theoretical calculation and experiments also. The formula that it follows is more or less exponential. And the length scale over which the Cooper pair actually decays. Decays means there is no superconducting correlation after that. So it's like is the length over which the Cooper pair can survive in a normal metal. So that is of the order of 100 nanometer, which is quite large if the material is normal metal. However, if you see the bottom picture, so there is what we have done here is a superconductor next to a ferromagnet. That is the situation now. So in that case, as per theoretical calculation and experiment also, the length scale over up to which the Cooper pair can penetrate, so is only up to 1 to 3 nanometers, which is, I'm talking about strong ferromagnets. Ferromagnets like cobalt, nickel, and all these things are well-known ferromagnets. So, so 1 to 3 nanometer, if the supercurrent dies in a ferromagnet in 1 to 3 nanometer, it's of no use. You can really never use it as in an actual device. So the motive is, can we increase this? So that is one thing, and that is one aspect of this problem. But other aspect is that one interesting thing. There are some more interesting physics also comes into picture when you put this together. You see the red line that I have put. You see the red line. So you see the red line that I have put in the second picture. So the order parameter, the amplitude of this current order parameter inside the ferromagnet, it actually oscillates. It doesn't go exponential like in a normal metal. So that process that depends on why that happens, because you can see there on the right hand side I have put delta P. So as the Cooper pair enters into the ferromagnet, it gains a little momentum. As such, inside the superconductor, it has zero momentum because Cooper pairs are made of plus K minus K. Okay, I told it's a momentum space pairing. So the net momentum of a Cooper pair inside superconductor, zero. But as soon as it enters into the ferromagnet, what happens is that, so there is an exchange field of the ferromagnet, which is Ex in this formula, okay. So because of that exchange field, so a net change in momentum comes up in the Cooper pair. And that net change, actually, if a change in momentum leads to a change in phase as the Cooper pair goes into the ferromagnet, and that change in phase leads to the oscillation of the order parameter inside the ferromagnet. Okay, you notice what I'm saying. So I'm saying there is a little bit of superconductivity inside the ferromagnetic, very thin layer, but it is there. But it is not, superconducting order is not smooth, unlike in normal metal. Okay, so it goes through some oscillations. So that is the interesting part. So this is another aspect. It's actually from 95 to 2005, proximity effect was in superconducting proximity for entirely dominated by this effect, which is called zero pi oscillations. These are okay. So this is an interesting thing. So a lot of experiments have happened. It is conclusively now demonstrated that this is true, and the signature of this effect, this zero pi oscillation of superconducting order parameter in a ferromagnet, is essentially if you make a junction, let's say. So let's say I make a junction, which junction means a superconductor ferromagnet superconductor junction, in which I put the superconductor here, let's say, in this, very close to the first superconductor. So when the red line is in the positive side, so then the coupling between this superconductor and the next other superconductor will be positive. So that is the zero state, so-called. But if I make the thickness such that the next superconductor is placed somewhere here, okay, so the gap is this much. So then it is when the phase is negative here, okay, phase of the. So then it is called in the pi state. So then the Josephson current, which I will probably not introduce. So if in the zero state, if the Josephson current is from one side to other, positive left to right, so then in the pi state, the current will be right to left and so on. So this has, I mean, some experimental verification people have done in a various ways. They can see, people, you can study the transition temperature of the tri-layer system. So that will show this 0 pi oscillation. You can study the critical current of the system. That will also show the 0 pi oscillations and so on. So, okay, so this is an interesting effect, but what I want you to take from this is that in normal metal, superconductor can go into a long distance. In ferromagnet, it can go to a very short distance. So we want to increase this. How can we do that? So what is the way forward for that? So I'm going to slide number 13 now. So so this is a bit technical, but I think students with a little quantum mechanics background can definitely understand this. So there is the Cooper pair is as such the allowed symmetry of the Cooper pair is given in this table. So what I have seen is for a BCS superconductor like BCS Coopers, like BCS pairs. So that is up and down. So the S is equal to 0, L equal to 0. So that is the thing. So that is allowed. But in some special cases, okay, in some special cases, what you can have is that you can have a wave function which is valid at L equal to 0 and S equal to 1. Okay, so that is also, and L equal to 1 and S is equal to 0 also. So that means not only up down in terms of physical meaning, so not only up down pairing is allowed, but also spin triplet pairing is allowed. Okay, when I say spin triplet, it means it has, I mean, 3 components. It can have up, it can have down, it can have a up-down component. Okay, so so this spin triplet, if it is triplet, then what you can see is that if it is triplet already, so it can have up, it can have down, and it can have up-down. So up-down has probably less useful in this case, but let's say it is up. Okay, so that means this up triplet pairs, they can go a long way into the ferromagnet. Ferromagnet is what is trying to make is all spins up, or down. Okay, and Cooper pair was not able to go because one was up, one was down in the pair. Now, if you have a pairing with up, it should be able to go. So that is, I mean, in a very basic way. I mean, it's a very loose way of putting it, but I think that sends the message what I'm trying to say. So if we can find spin triplet supercurrent, then it can solve the range issue inside a ferromagnet. Okay. So the general recipe, I mean, I think you can look at this review of modern physics. It explains nicely this Burge. So this is the process by which a singlet current can be converted into a triplet supercurrent, singlet supercurrent into triplet supercurrent. So that was predicted by this Burge, Volkov, and Epitov, and it was experimentally also demonstrated that actually if you have this kind of arrangement, then supercurrent can go a long way into the ferromagnet. So you can see the comparison here from this experiment people have done. This was the first experimental confirmation actually. Sorry, so this was only in 2010. So it is pretty recent in a way. So it's okay. So the recipe that the theoretical physicists gave is that you need a way of spin mixing and spin rotation to convert a spin singlet into the spin triplet supercurrent. Spin triplet we need for spintronics. Okay, that is why we are doing all sorts of things. So what these people use, if you are able to see slide number 15, in which there is device is shown on the left hand side. So you can see, so there are many structures, but what is important is this F layer. this F layer. Bottom layer is S, then F, then S, right? So this is the active layer, let's say. So this F layer is actually not a single ferromagnet. If you see it is written here, what is the F layer consisting of? So the entire thing is the F layer. Okay. So there is one, it's a combination of several ferromagnetic material. There is cobalt in the middle, and there is X, and then there is copper and ruthenium is also there. So, but the purpose of this is to use the recipe given by these theoretical phases. So they have told that you do some way of spin mixing and then do something to do the spin rotation of the Cooper pair. Then you will be able to get triplet. So that is what they have tried to do by putting this, all the combination of things. On the right hand side, you see that when you introduce both these effects by putting this X is equal to X is a material which is PD nickel, palladium nickel. When you do that, you can see the red line, red dots. Okay, so red dots are actually going quite along. So the y-axis is the current, critical current essentially, and the x-axis is the thickness of the ferromagnetic layer, which is cobalt, DCO, okay, this middle cobalt layer. So in normal condition, so it is decaying within, let's say, it's going like few orders of magnitude lower in 20 nanometer. But if you see that when you put this PDNI layer, which is facilitating the spin mixing effect, it is able to, the current is able to sustain up to, at the same order, like not much change in current up to 30 nanometer. So it's a huge result in this field. Okay, so it means is that critical current, the superconducting current, is going 30 nanometer without loss into the ferromagnet, which is good. So 30 nanometer is kind of in an accessible range, in which you can actually make devices. So that is why it is important to increase this range as much as possible, so that you can make usable devices. That is the okay. So this is the recipe. So this was the demonstration. There are several other demonstrations people have also done. So I'll skip. Okay. So this slide, I'll just the top part you probably don't. So the recipe is essentially what we thought. This is one of the experiments that we did in these directions in our lab. Is that what we can use for spin rotation and spin mixing. So what we thought is that each ferromagnet has a domain wall. Many domain walls. Okay. Domain walls are naturally systems in which the moment naturally rotates around some axis. If it is a needle wall, it is rotating like this. If it is a block wall, it is rotating like this. So it is. So this is a naturally available source of spin rotation. Okay. So if I am able to push a Cooper pair through a domain wall, okay, let's say a singlet Cooper pair through a domain wall, it should naturally be able to convert to triplet, because of the spin rotation provided by the domain wall itself, which is built in. We don't have to make any devices. If you see in this device, they had to make a complicated multi-layer of materials to achieve this effect. Okay, but if you have a domain wall, you already are getting it. The built-in rotation is there. Moment is rotating built, so that. We thought maybe it may be useful. So we actually did the experiment and found that in this kind of device, I have shown on the top here, that actually if you have a domain wall, so it and the top layer in this picture is actually superconductor. Bottom second layer is a nickel. Niobium is the superconductor. Nickel is the ferromagnet, and there is a gap you can see. So there is no way the superconductor can directly go from here to it. It has to go through the nickel. So when it goes through the nickel, it goes through a domain wall. If we make it go through a domain wall, so then it can be triplet. Okay, so it can be converted to triplet because, and this effect actually we made a small device also of the order of, you can see this device is made of something like what is the scale? It's like less than a micron scale device. And we did some simulations also to show that actually this is possible to, if you make a kind of constricted structure of the ferromagnet like this, then it will be, you can pin a magnetic domain wall at the gap. So that is the requirement. So unless you have a domain wall at the gap, there will be no current from one side to other side, no supercurrent. I mean, we want supercurrent from one side to other side. Okay. And if it is a normal supercurrent, normal means singlet supercurrent would not be able to go beyond few nanometers because the ferromagnet is actually nickel, which is very strong. So, but what we see is that when we have anti-parallel configuration of, I mean, you can see the simulations actually. The right-hand side simulation you can see. The next to the constriction, one side is red, one side is blue. So that means the domain, one side is in one way, other side is in other way. So that means it's a wall. So it's the constricted region is a wall. Okay. Whereas on the left side simulation, you see that the constricted region, on the both sides of the constricted region, there are. So in these two configurations, we saw that when we do that in experiment, when there is a domain wall, we are able to send a current, okay, and the resistance is low. When there is not a domain wall at the constriction, then the resistance is high. So that is, I mean, a signature of what I mean, people have shown in different ways that we can actually use a natural domain wall also to generate the required spin triplet supercurrent. Okay, so that is one. Okay, so that is one aspect that I talked about. What about so the another issue that I pointed out in the beginning is that the interface issue in any multilayer system, it's always there. Okay, so what to do about it? So what we thought is, can we make a very sharp superconductor ferromagnet interface, very natural interface? So for that, what we have to do, so we have to find a superconductor which is based on a ferromagnet. Okay, so then if the superconductor is naturally going on a ferromagnet, then it will be a suitable material. So what I found is that one suitable material, which is nickel bismuth 3. Okay, so we are moving into another topic now from the previous one. Okay, so we're talking about the interface issues, how to solve that. So for that, we try to explore a material, and we found that the nickel bismuth is one possible material. You can see initially the general concept is what the superconductor ferromagnet. I mean, okay, it's not going well with each other. But what we see is that if you put nickel and bismuth next to each other, you just deposit a layer of nickel and then deposit a layer of bismuth on that. Okay, so then at the interface, it naturally grows a superconductor, which is like nickel bismuth 3. Okay, this phase nickel bismuth 3. So this automatically grows. So which is there is a process for it. It's called reaction diffusion mechanism. I'm at slide 21 now. So what happens is what you see in this picture is that one side is nickel atoms, other side is bismuth atoms. But bismuth has a low melting temperature. Okay, so it is in terms of even at room temperature, if you see, the mobility of bismuth is high compared to other material like nickel, which has the very high melting temperature. So what happens is that when you put them together, there is a diffusion mechanism, which also it's called in the process of diffusion, it also reacts. Okay, if it reacts, it makes nickel. This is let me put it again that this is an automatic process. You just deposit the sample. You are doing nothing. You deposit 2 layers, keep it, no heating, nothing. So this is a self-driven diffusion, which then leads to a reaction, and then that reaction limits how far the diffusion can happen. Okay. So what we found is that if you put 2 layers together like this, you will have certain thickness of nickel bismuth, which will show superconductivity, which does show superconductivity. Okay, so actually we have done a lot of work on this nickel bismuth bismuth 3. So what is the advantage of this? We are talking about interface, right? So that is where the so interface is when see this this middle layer is nickel bismuth, which is a naturally grown nickel superconductor, and just the next atom, which on the left hand side, just the next atom is nickel. So that means is the interface of nickel superconductor and ferromagnet is atomically smooth, atomically I mean it's precise. Okay. So, so diffusion will happen into some certain up to certain length inside the nickel, and then that area has formed a superconductor, and just next to the superconductor, the atoms are all like nickel. So it's a ferromagnet. So it's like interfaces. There is no chance of contamination of the interfaces because it is growing there. So we see that okay. So that is actually so we saw that the TC can be as high as 4.2 Kelvin, which is not bad. I mean, in terms of the devices that we work to see quantum effects and all, 4.2 K is very accessible temperature. So measurement wise, it is not that bad. In this, when we did it with different thickness of nickel layer, so what we saw is that you remember I mentioned earlier, so this 0 pi effect, 0 pi transition. So depend x-axis is now my thickness of nickel layer, y-axis is my TC. TC means transition temperature. So transition temperature also shows the signature of 0 pi transitions I mentioned earlier. So transition temperature goes up and down as a function of thickness of the ferromagnetic layer. Okay, so that means Cooper pairs are able to go into that far into the ferromagnet. So you can see the length scale over which it is able to go into the superconductor, into the ferromagnet. So you see up to 25 nanometer. We have been able to measure 25. I don't know. I mean, after that, probably the effect died out. But up to 25 nanometer, in earlier reports people have done in nickel, it was few nanometers. So, I mean, when you deposit something, some niobium on nickel and make a device and do this measurement, you will see it will the 0 pi transitions will be there, but it will be constricted to 3 nanometer, 4 nanometer. So that is 5 nanometer maximum. Okay, but here we see up to 25 nanometer. Okay, so it's a big advantage in a way. Superconductor, at least superconductor is going into the ferromagnet quite a long distance. Okay, and why is that? Because we have the difference is that the interface here is very natural. It's like an atomically smooth interface. So that plays a big role in effective transfer of Cooper pairs into the ferromagnet without much scattering. Okay, so that is one of the findings of our group. How to take it forward? That is another question. How to take it forward into a real spintronic device? That is okay. I mean that is still a matter of research, but there is a way forward. Okay. Okay, so I think so that is what I had for today. So what I and overall the goal of this short presentation was to impress upon you the fact that although the general feeling is that superconductor ferromagnet don't go well with each other, but when you put them together, a lot of interesting physics comes in, and there is a new field, entirely new field coming up on superconducting spintronics, which actually requires superconductors and ferromagnets to be put together. Okay, so I think with this I'll take a few questions if anybody has. Okay, thank you.
Thank you, sir, for elaborating quantum phenomena. So now it's open for the questions. Let's see if someone asks from the sir. I don't see any questions in the chat box, but I want to ask you some questions related to the slide where you showed some allowed state.
Yes.
In triplet current and all. So can you that slide?
This one.
Yes.
This one.
You mentioned something about fermions here. Which I mean, the Cooper pair acts like a boson, right?
Yes, yes, yes. But the net wave function will be written on this is a fermion wave function. I mean, the net wave function is see. I mean, it's a correlation function essentially. It is required here is that f. You can see R1, R2, S1, S2, T1, T2. So this is about two. Yeah, it's a pair correlation function.
Okay.
It's a pair correlation.
Why we need a spin triplet current for the synchronic application?
The reason is spin singlet current will not be able to go into the ferromagnet at all. So if it doesn't go into the ferromagnet, we cannot use it in spintronics. That is because spintronics is already ferromagnet based mostly. Okay. So unless the current is not able to go into the ferromagnet, how will you use it? So that is why we need to find a way to have triplet current. So that is.
That means its coherence is more for spin triplet. I mean,
so spin triplet, it's inside the ferromagnet. It can sustain a longer distance. That is because it is like up. Okay, in a crude language, let's say it is up. So it is not like up down, which is breaking into the ferromagnet. Okay.
Because the other side is also parallel. Yes.
Exactly, all parallel. Okay, so Devakant, you wanted to ask something.
Kartikeswar, I just want to ask one thing. We are putting a complex structure. We are putting this magnet is inhomogeneity or domain wall. All these things we are doing to get the triplet component. Am I right?
Yes.
Yeah. So this instead of doing all these complex things, I just want to know how if you just put a triplets like you are showing na SR2 RuO4 something like that. If you start with that one.
You can. So thing is, so that is a different thing. So if you have, for spintronics, you need polarized current. So if it can give a triplet current already, so that is good. But then with our technology, let's say whatever spintronics has been developed, so it is all like metal based. So if you want a like LSMO or all that based spintronics, the oxide based spintronics.
Oh, sorry.
Then I think.
Yeah.
Okay.
So the interface making will be very difficult because they are not compatible.
Yes.
Okay. Thank you.
So, okay. So there is, I think there is some question from Sujit Verma. Is there any temperature variation issues during deposition nickel and bismuth? Temperature variation issue. So can you speak up? I mean, I am not getting it actually.
Sujit, are you there?
I think he's probably typing. Okay, so I mean during deposition, let me clarify if I am getting it correct. During deposition, we are not changing the temperature, so it is everything room temperature. Okay, so still the diffusion happens. It's called reaction diffusion mechanism. It happens. It's a known phenomenon. It's not like it's new, but what is interesting is that a ferromagnet grows a superconductor, which is interesting. Okay, so
one more question from me. In this superconductor and ferromagnet junction, suppose you are making the junction, so what should be the minimum interface thickness?
Interface. Okay, so if it is if it is a singlet junction, then you cannot make the thickness more than 2-3 nanometer because there will be no current across it. Okay. But if it is triplet, you can make 50-70 nanometer. So I showed a device of a very small device, which was actually 70 nanometer of ferromagnetic gap. Okay, from one side of the superconductor to the other side. Okay, so the current was able to go, super current was able to go through a strong ferromagnet across a 70 nanometer distance, which is not possible if it is singlet, if it is up-down pair. No, if it is possible only if because by the domain wall we are making it up. Okay.
Okay, if there are no questions, let's thank once again Professor Senapati for his very beautiful talk.
Thank you.
With
Okay,
this,
thank you very much.
thank you very much.
Okay, sir. Okay, I'll log out now. Okay, thank you. Thanks to all.
So tomorrow, once again, we'll meet at 11 o'clock. And tomorrow is the last day of our lecture series. Thank you.